Next up, we have smea talking about real penetration testing. Please give him a warm welcome.
All right. Hi, everyone. As mentioned, I'm smea, and today I will be talking about how to hack a butt plug. This is one of those, just FYI. I don't know if you've ever seen one in person. I had not. But I've been introduced to a lot of things over the past 2 years, so, you know, here we are. You might be wondering, what is it like, what does it even mean to hack a butt plug? Because, you know, if you take a look at this, it's basically just like a piece of silicone. Obviously, you're supposed to put it somewhere. There's not much to it, right? You don't really need any electronics in here. But over the past couple of years, or a couple of years, I mean like past few decades even, actually, there's been the emergence of this new field called teledildonics. Look at the etymology for this. You know, it's from the Greek tele, which means from afar, and the English dildo, which apparently just means dildo. There's no origin. I tried to look it up. No one knows where this word came from. But yeah, it's pretty self-explanatory, right? The idea is that you want to make sex toys that are controllable remotely in some way. And that actually, you know, enables a number of different scenarios. Basically, I just want to explain to you, because not everyone is familiar with this field, okay? Just want to explain how this works. So you take this butt plug, right? You insert it. And from there, you're actually able to like control it from your phone, from your laptop, from any kind of device really. So that's the first scenario. Second scenario is like technically kind of the same thing. It's just you end up giving control to, you know, someone else. No, this is an actual thing, and so they actually advertise this for like, oh, you can like go out to the bar and like no one will know. It's kind of fun, but technically it's like the exact same thing. It's just it opens up, you know, a new kind of attack scenario because you're giving control over to possibly a stranger or, you know, someone else, which does change the threat model here. The third scenario is going to be the same thing. You give control over to someone else, but this time it's going to be over the internet. And you know, you can kind of think of that as it's probably not going to be a stranger, but it might be. It's going to be enabling people in long distance relationships possibly to have some fun, which is pretty cool. But where the real money is actually with using this as a sex worker. And I'm not trying to make a joke out of this. Like, people actually do rely on these things as tools to make a living, right? And in my opinion, this actually is something that kind of gives some legitimacy to this research, because, you know, I'm just hacking butt plugs. Yes, it's funny, but people do actually make a livelihood off of this, right? It's like some scenarios are going to be, you know, cam girls, cam boys, whatever you want to call them, people who basically provide dynamic, you know, sex entertainment over the internet, are getting paid to have people watch them, and they sometimes have the ability to, you know, get paid to give control over to their sex toy. The company that makes this butt plug actually has a patent on the concept of tipping money over the internet to control a butt plug, which, you know, that's a whole other debate, but it's kind of interesting. One of the scenarios also is like you can either, have it vibrate in exchange for, you know, a $5 tip or something, but it can also be you create a link to control your butt plug and you give it out to someone on Twitter or someone on whatever, just to give them control for a limited amount of time. So people actually do, you know, rely on these as tools for their work. So it's kind of important, in my opinion, to take a look at what the security posture is here. And so the security posture, like, let's think about scenarios that are interesting for us in terms of hacking these butt plugs. One of them is just going to be, okay, well, you're using this locally and someone is within the vicinity, notices that you have a butt plug in and tries to hijack that connection. There's actually already been a bunch of research into this, so this is not going to be our primary focus here, but it is definitely a scenario that is kind of interesting. We will note that, you know, doing this might technically be sexual assault. I don't know. It's problematic. Please don't do it. Whether it's legal or not, just don't be a dick. Second scenario that's kind of interesting is going to be looking at doing the exact same thing but remotely, right? As I mentioned, in some cases, especially if you're making money off of this, you might be giving control over of your sex toy to a complete stranger. What does that mean? Are they going to be able to, you know, compromise your devices or compromise your butt plug or do whatever, do something bad? So that's a compromise scenario that's totally legit and more interesting, in my opinion, and kind of what we're going to be focusing on. And the third compromising scenario would be the opposite, thinking about having someone who has a hostile butt plug, basically. who might be able to hack back into your computer or into your phone or whatever, and then possibly hack into whoever is connected on the other end. Which is the other scenario that I don't think people realize this is a real risk of, the hostile butt plugs in this world. So this is something that we will be exploring. Taking a look in practice, now that we've, introduced the whole world of teledildonics, what does it look like in practice? This is 11's Hush, which I will be doing a live demo on later on, just FYI. It's built as the world's first teledildonic butt plug. As mentioned, it's a butt plug. I'm going to just be saying butt plug a lot in this talk, just FYI. And you can control it from your phone. It has an iOS app, an Android app. You can control it from your computer. It works on Mac OS and Windows. And on Windows, you actually do need to use a special USB dongle, which I would show you, but it's plugged into my computer right now. So that dongle is made by 11, so the same company that makes these butt plugs. And yeah, it's like $5. It's kind of interesting. We were going to look into that. And then, the app actually introduces social features, so you can chat, video chat, send pictures, and then obviously give control to your butt plug over to someone else. So in terms of the, kind of like the threat map, in my mind, this is what it looks like if you're thinking about the PC app. So you have a BLE connection between the butt plug and the dongle, and then the dongle obviously is connected over USB, and so on, right? So the question here is what does it look like for each compromise scenario? Well, for the local case is just compromise scenario 1, just want to compromise that BLE connection. Again, there's already been research in this. Basically there's no security there. Anyone can kind of just hijack that connection. There was a great talk last year about a tool called BTLE Jack, which you can just totally use to take over this. So that's not what we're going to focus on. The second kind of scenario for compromise was over the internet, so it would be kind of hijacking that connection somewhere or thinking about seeing how you can compromise one app from the other. And the third scenario is going to be trying to hack into the butt plug, trying to hack into the dongle, trying to hack into the app, each from one to the other. And so that actually involves a lot more research. The question is, this is a butt plug. Obviously, it's, well, I mean, not obviously. There is actually an open source butt plug project, apparently. No, I'm not making a joke. It's apparently good work. So the question is, well, where do we start, right? I started working on this, and I was like, well, I don't have the code for a butt plug. I don't have the code for the dongle. So what do? Well, the PC app, you can just download it and put it into IDA and see what happens. Turns out you actually don't even need to put it into IDA because of course it's a multi-platform app. It works on both Windows and Mac OS, so of course it's an Electron app. So of course everything is written out in JavaScript. I don't love JavaScript, but the nice thing about it is that it does end up still having a bunch of variable names, a bunch of field names for these objects. So it is kind of easy to reverse engineer. It is obfuscated, but you can just throw it into a beautifier and try to figure out how things are going. And yeah, so once you've done that, you can just kind of like start looking for how the dongle works. Turns out it's just a serial port connection over USB. And that allows you to start then sniffing the connection between the dongle and the app. And one thing that you will notice, the sniffing data is on the right here, is that all these messages being sent between the dongle and the computer app are all in JSON, which is kind of interesting because well, JSON is obviously, native for JavaScript apps and stuff, so that's convenient. However, for a USB dongle that is just basically a, 32-bit microcontroller, it's kind of weird to have to embed a JSON parser in there. And for us, it's a good thing though, because JSON parsers, it's a parser. There will probably be a bug in there. Turns out there is a bug in there. But it's kind of annoying to take a look at that without having the code of the actual dongle. However, since we do have the code of the app, we can take a look at the update mechanism because they have firmware updates for the USB dongle. From there you can find the URL from which to download that firmware and download it and see if it's encrypted or signed or anything. Turns out it's none of these things, so you can just grab it, unzip it, throw it into IDA and see what it looks like. From there we can kind of notice that it's thumb code, so it's pretty classic ARM firmware code. Throw it into IDA, you can kind of see how it looks, start reverse engineering. Notice two things. First thing is it has two command handlers over USB serial. One of them is like these simple commands such as reset or like asking for device type, stuff like that. The other one is it basically if it doesn't find a simple command is going to throw into a JSON parser, which is what we expected, and that's where we can start looking for bugs. One thing that is interesting is in the process simple commands function is that it does have a command for DFU, so that's device firmware update. So as expected, we do actually have the ability to send these commands and get it into firmware update mode. But looking at the JSON parser, which is what we're interested in here, of course we end up finding a bug. The bug is in this function called parse JSON string. Basically that function is just supposed to allocate a new buffer, copy the initial string into into that new buffer, while also handling things like escape sequences. The problem is the way that it works is first it calculates the length of the new buffer that's going to allocate, then it allocates it, and then does that copy. And so of course there's a mismatch between the length that it calculates and the length that it's going to actually use at the end there. The way that works is that it supports the U escape character sequence, which takes 5 parameters instead of just 0 as it expects. And so because of that, we're actually able to kind of escape the null terminator and make it such that the string length that was calculated first is wrong. This is a little animation here. What's going on here is that it starts calculating the length. It runs into this escape character, so it skips the character, and then it finds the null terminator, and that's the string length that it's calculating. Then in this loop that actually copies into that buffer, what happens is it runs into the escape character sequence. So it says, okay, there's a backslash, there's a U. That means that I need to skip 6 characters. And so it's actually skipping over the null terminator, which is a problem. And then it just kind of keeps going. And it's going to be copying all these characters into that buffer, which is only 6 bytes in length. So obviously there's a problem. We can overflow out of this buffer and kind of just get code execution that way. This is great. We do have this bug. At this point, we don't actually know what the hardware is running. We don't know, if it has dep or anything like that, which kind of complicates exploitation. So we do know there's no ASLR, there's no stack cookies, so it's basically hacking like 1999, assuming there's no dep, which is pretty cool. Turns out the stock is just a Nordic Semiconductor stock, very classic stock used in a bunch of BLE IoT devices. The nice thing is they also left us a bunch of debugging pads, so we can just connect to it, solder a couple things, and all of a sudden we can just debug this dongle, which is pretty great. Being able to debug the dongle, we can kind of dump the contents of the heap, see what's there. Turns out the heap is only used for the JSON allocators, JSON parser, so that's not super great, but it does also include metadata. So what you're going to see here is that for each allocation you have a length field as well as a next pointer for the free list, assuming the allocation has been freed. So the easy thing here is that yes, we can use our overflow to corrupt a length field, put it to be 0. That way, and then corrupt the next pointer field. That way, the next allocation, assuming the pointer field points to a non-zero or like a big enough value, will be placed there. And since we can place the allocation there and then copy a new string into it, it's very easy for us to use this to basically write arbitrary data in arbitrary location. We can do this while the debugger connected, and as you can see on the right here, we have the stack basically is being dumped, and the stack has been completely overridden with just A characters. That gives us code execution on the USB dongle, and that's pretty cool. From there, we unfortunately remember that there was a DFU mode on the dongle all along. And the DFU mode, I would expect, coming from a video game hacking background, I expected the DFU, like the device firmware update mode, to just kind of, authenticate the update in any possible way. Turns out it kind of does with a CRC16, which, if you know anything about crypto, is not any kind of authentication. I don't think that they actually wanted to have authentication there. They just kind of figured that, well, who cares about getting, code execution on a USB butt plug dongle? Turns out I do. So that's unfortunate. But it is interesting. At this point, basically, we have 2 different ways of getting code execution on this dongle, and the JSON parser way, that I mentioned, I spent a lot of time on it, might not seem very useful because we have a device firmware update mode, but it turns out is actually going to come up again later with another vulnerability that we're going to chain together. So, I didn't just say all that for nothing. Point is, we can get code execution, we can flash on firmware, which is pretty great. So at this point we have compromised the USB dongle from the PC app, which is like, yay, that was definitely the easiest part. From here, what we want to do, since we have control of the dongle in theory, we should be able, we want to figure out a way to somehow get code execution on the butt plug, because that's kind of what we do. Looking at the hardware on the butt plug, turns out that there was a debugger on the dongle, so it might make sense to take a look at it. It's a very similar SOC, so it's another Nordic Semiconductor SOC. It's a little beefier. It's an M4 instead of an MM0. It has more flash, has more RAM. It's pretty great. but it is the same technology basically, just more up to date. So the nice thing is, yeah, we can expect that there won't be any depth, there won't be any like more advanced mitigations on the dongle, so that's pretty easy. From there, there's a bunch of other things that were not on the USB dongle board, but there are a few things that were, which is the SWD test points. So with that, we can actually debug a butt plug, and this is what it looks like in practice. I'm kind of terrible at soldering, but I do have a bunch of butt plugs like this that are opened in my bag. So, you know, I don't know why I'm telling you this, but this is pretty cool. From there, the nice thing about being able to debug a butt plug is that you can actually use this to dump the firmware. And from there, you know, kind of figured that if the dongle update mode was so insecure, maybe the butt plug also has an update mode which is also super insecure. It turns out that yes, it does. If you send in the exact same DFU command that you sent to the dongle, it will also go into device firmware update mode. And from there, there's actually an app that Nordic ships, which is the NRF Toolkit app or Toolbox app. It will just let you flash new firmware to it. At this point, we don't actually know if the DFU mode is as insecure as on the dongle. It could have been that they implemented, asymmetrical keys to kind of authenticate the firmware. Of course, fortunately for us, they didn't. So you can just kind of dump the butt plug firmware from SWD, modify it, compute the new CRC16, and send it over. And this way, you can see on the right here is you have Wireshark. A little Wireshark trace here that kind of just has the butt plug sending back a little message saying hello from plug, which means that yes, we just got code execution on the butt plug by not even doing anything. There's no vulnerability here. It's just kind of by design you can reflash it, which might be Levin's attempt to like open up to the open source community. It's possible. It's unlikely. But the point is, anyone who can connect to your butt plug at this point can get code execution on it. Which seems kind of dangerous. At this point, we do still require being local, like being in the physical vicinity of the butt plug to get code execution on it. So it's probably not as big a deal as you would want it to be, but it's still a good question of being like, okay, we have code execution on the butt plug, what can we do with this? Well, there's a few ideas that I had. The first one is if you can get code execution on the butt plug, you can actually create butt plug ransomware. You modify that firmware, you make it such that the DFU mode can't be enabled until you give it a certain key or something, and then you just disable all the code that creates vibrations, and yeah, you have your own ransomware. You can ask maybe for like $50 to unlock it and protect it from future butt plug ransomware, kind of butt plug vaccine, if you will. So this is one scenario that could work. Another scenario that is kind of interesting, but I did not really look into that much, is the idea of like weaponizing a butt plug or any other sex toy like physically. And in the case of the butt plug, it really just has one motor and a little battery. Well, like a pretty big battery actually. Like I guess probably 80% of the butt plug is battery. So the question is, I don't know if you remember like what happened with all these Samsung Galaxy Note phones, where they were like just kind of blowing up. Well, it might, possibly be possible to, Again, I'm not an electrical engineer. I don't know if this is actually possible. It probably isn't, but if it was, this would be bad. I'm going to assume that this is not possible, but it's something that is worth thinking about because you do have actually a lot of other sex toys that have other things in the motor, right? You have sex toys that apparently have. I was looking at the code of the app and looking at all the different commands that work for different sex toys. There's a command that just says rotate. So clearly, there's some kind of moving part in this sex toy. And I'm wondering, maybe there's like a safety feature for that motor that is actually encoded in the software, right, instead of in the hardware. So getting code execution on it could have bad consequences. Same thing, I think there's like another sex toy that has some kind of air pump, which seems dangerous, but I don't actually know if it could be problematic. So it's something that's worth looking into. And finally, we do have our last thing, which is the hostile butt plug. Hostile in terms not of exploding your butt, but as much as kind of trying to hack into your other devices. So that is something that's worth thinking about, and that's what we're going to be looking into. It's like, okay, we have code execution on this. We know we can do ransomware, but can we start hacking other devices from our butt plug? Of course, the answer is going to be yes, but for now, I'm going to pretend that we don't know that. So, interestingly, at this point, we have code execution on the butt plug. We have to figure out if we can get code execution in the app from that butt plug. So doing that is as simple as trying to look into the way that the app kind of handles incoming messages, right? So the first thing, so this is like the callback on the left in JavaScript. I guess this is how it works to talk over serial ports in an Electron app. And what it does is it gets N is like the incoming data, throws it into, it casts it to a string, and then it throws it to a bunch of different functions. The first function is find dongle, which basically just handles one of the initialization messages that comes from the dongle. The second one is on data, so this is like the actual main command response handling loop, handling function. And what it does is, it takes this incoming JSON blob, which can only be up to 32 characters in length, by the way. I'm not sure why I didn't mention that earlier. It's going to come up in just a few minutes. So it's just going to parse that, and it's going to then use it to do whatever. It doesn't actually do a lot of processing on this. It's just basically going to like stir compare it to something, be like, oh, what's your status? Like, what's your battery life and stuff like that. And the last function that it calls into is actually much more interesting for us. Surprisingly, it's much more interesting. I called it debug log. It doesn't really have a name in the actual code. But what it does is it logs the whatever's incoming, like the serial data. It throws it to the console.error function. So it prints it out to console as an error messages for some reason. But what it also does is it creates a new DOM element, like an HTML element, and it throws the entire contents that it just received over serial into that element as HTML. Now, I'm not a web dev, but if you are, you will probably think that this is a massive cross-site scripting vulnerability from a buttplug dongle. So from there, basically, if you have control over the dongle and you can send anything over serial, you can actually get the Electron app to interpret that anything as being HTML. That's problematic because HTML will have the ability to spawn new JavaScript code, and new JavaScript code in an Electron app basically is just, you just compromise the computer because there's no sandboxing or anything. So the question is, can we actually do that with our limitation of having only 32 characters at a time? Turns out, yes, absolutely, we can absolutely do that. One of the ways of doing it is what I was showing on the right up there. You have an image tag with a source that doesn't exist, and then you have the on-error callback, which is going to be called whenever it can't actually be loaded. And so the screenshot is just showing that plugging in this malicious dongle is going to allow you to execute JavaScript code in the app. So that's problematic. It's kind of annoying to get a huge payload just because of the fact that we can only do 32 characters at a time. It's entirely possible. So at this point, we've actually compromised the app from the USB dongle. So we're halfway there to kind of make it back to from our butt plug to the app, which is pretty cool. Now, of course, the question is, because what the dongle does essentially is just act as a little bridge between the dongle, between the butt plug and the app. The question is whether we can just use the exact same vulnerability to compromise the app from the butt plug directly. Unfortunately, the answer to that is no, and the reason is that we have another character length limitation on the messages that are coming from the butt plug to the app. The way it does this is on the right you have this code that is in the dongle firmware. What it does is just grabs the incoming data. If it sees that it's more than 20 characters, it just kind of cuts it there and copies it into the new buffer. Now, a new buffer is actually on the stack, and there's actually a vulnerability there, which is that they don't null terminate that string. So if you're able to place some uninitialized data after the string, you can actually send more than 20 characters up to the app. Unfortunately, I did not find a way to actually exploit this, but it is kind of vulnerability, so it's worth keeping in mind. So, problem here is, we can't actually use this to get code execution directly on the app from the butt plug, which is kind of sad. But, it's kind of sad for one thing. What's also kind of sad is that if you took a look at that code there, it basically doesn't really do anything with the input. It literally just copy pastes it into a new string and sends that new string up. So we can't really find any kind of memory corruption vulnerabilities in the actual butt plug specific code. However, the one thing that's pretty cool is that there's way more code on this microcontroller than just the butt plug specific code that was written by 11s. There's also this whole soft device region, which is at the bottom of memory. It's based at 0. And so what this soft device is basically a driver for that SOC that was written by Nordic Semiconductors themselves. And so it's going to contain everything that you need to interface with the hardware without having to rewrite everything yourself. And so that's going to include the BLE stack, so all the code that is going to handle the Bluetooth Low Energy protocol. And so it might be possible for us to take a look at that, kind of reverse engineer it, because obviously it's not open source, and find a vulnerability in the Bluetooth Low Energy stack. That's just what we did. In order to hack a butt plug, we were finding Bluetooth vulnerabilities. And yeah, so because we can kind of debug it, debug that butt plug or the dongle firmware, it's actually really easy to kind of just like follow the flow of data, because there's also no ASLR, and then it's really easy to define the code that is going to be handling those messages. And on the right here, we actually have one of those functions that handles these incoming messages for the general attribute protocol for central mode messages, I guess. And so what I'm showing specifically is actually the handler for one of the specific commands in that protocol, which is the read by type command, which, as I understand it, because I'm not really a Bluetooth expert, it's something that is going to allow you to kind of request reading attribute handle data pairs back from that device. So essentially, you ask read by type to your peripheral device, giving it a certain type, and it's going to return all the handles for all the attribute services that are associated with that type. So what that means is that it's possible for it to actually receive more than one attribute at a time, and the size of each attribute, handle attribute data pair is encoded as a field inside of the packet. That means that we can actually control it. Now, if you look at the code, what it was doing in that function is that it has allocated on the stack a fixed length buffer for the attribute data. And that fixed length buffer is going to be a struct basically that has just the handle value and then a pointer to the data associated with that handle. So that's what you can kind of see with these little arrows there, is that, okay, actually, yeah. Oops, if you have these little arrows there, is that you're going to have at the bottom left there, that's the actual binary hex data that is inside of that buffer, and so you have the 0xD handle and then a pointer that points to that data, like the data in blue that is associated with it. And there's the same thing for the second handle and third handle, and because it's on the stack, no, actually, never mind. That's not a sentence that needs to be said. So, vulnerability here, if you read the code a little bit, what you're going to see is that, yeah, it reads that little purple field, length field from the incoming message, so that's completely controlled by a potential attacker. And if we look at what happens if we place value 0 there, basically you end up with an unbounded infinite loop. So that loop is, sorry. Because it's unbounded, it doesn't actually check that the data that's writing into the output buffer is within the output buffer. We have a very classic stack smash kind of vulnerability, which obviously is very unfortunate, because on these devices, once you can smash the stack because there's no stacker keys or ASLR or DEP or anything, you basically immediately have code execution. In this case, the problem is because you have value 0 there. In this specific case, it's actually going to be in completely infinite loop. So you're just going to overwrite all the data in RAM with garbage. Which is kind of unfortunate, because that's definitely going to crash and not going to be useful. But if you think about using value 1, it actually is going to be bounded by the number of bytes that are inside of the incoming message. And what that means is that you're going to be able to overflow ever so slightly from that buffer, and then from there, because it's a stack buffer that is based on the stack, you're going to be able to corrupt everything that's near it. So taking a look at before what happens when you do actually use this overflow on the stack. In yellow is going to be the attribute buffer that I was mentioning. Then in blue is going to be a bunch of saved registers, and orange is actually the return address. So that's kind of the things that you would want to be corrupting on the stack. And then you run this run the vulnerability, is going to overwrite all this data on the stack with, in this case, completely, well, it's going to write two things, right? It's going to write the handle data, which is actually only overwriting the less significant bytes of D words every 8 bytes, and then it's going to be writing a bunch of pointers to data that we control. So this is actually a pretty useful primitive for us. We can just kind of start corrupting everything. We can corrupt the return address with a pointer that points inside of our packets. And that's really great because basically that means that as soon as the function is going to return, it's going to execute code that is placed inside of our packet. So it's basically a backdoor packet if you think about it. It's going to just execute a piece of code you give it without really doing a lot of fuss, which is pretty cool. Thing is, the Cortex M0 CPU actually does not support ARM mode, so we do have an alignment requirement on that return address. It has to be, aligned to 2 plus 1, basically. So that is one problem, because if you look in this specific case, what was overridden on the stack is actually not aligned to that boundary. So this would actually crash, which is not great. There's another requirement that we have, which is that there are saved registers that actually local variables that we're overwriting on the way over that are used on the return path of this function. One of them specifically is actually used to be dereferenced at a 32-bit boundary. And so what happens is that if it's not actually aligned, it's just going to crash. So that's another thing that we have to take into account. And basically, that means that we're going to have to slide this packet over in the way that it's allocated if we want to have any hope of it actually being exploitable. Fortunately, that's really easy because the way that the soft device allocates these incoming packets is in some kind of ring buffer with absolutely no enforcement of any kind of alignment requirements. And so what that means is that if I send a packet at a certain length before or after, I can control the alignment of this packet that I'm going to be sending afterwards. So this is what you're kind of seeing in yellow and in blue are two packets that I'm being sent before the exploit packet is sent. And that allows me to control the alignment of that last packet and make it such that it is correctly aligned and not crashy, which is what we want. From there, the way that you actually exploit this to get code execution in a way that's useful and not just, not just executing two instructions and then returning is that I send a first packet which is going to contain a bunch of shellcode. Then I send another packet that's going to contain a bunch of data, another packet that's going to be containing a lot of data. Both of these are going to be used by the shellcode. And then a third packet which is going to be the one that actually triggers the vulnerability. The way that it works is that the one that triggers the vulnerability is going to execute a single instruction, which is what you see that C1 E7 instruction there. What that does is it jumps back into the green allocation, into the green packet, and then that one is going to execute this very simple piece of code, which is still loads a bunch of registers from the I think the blue packet, and then it's going to use that to call into a function, return cleanly, and then we can just send that packet over again. So that allows me to basically, by sending 4 packets, execute any arbitrary tiny piece of code within that remote dongle, and then return and do that over and over again. Which is very convenient because that way I can actually just call into memcopy and over and over and do that to copy a larger shellcode binary, and then we're going to jump into it, and that allows us to execute a lot more code. So at this point, we actually just have completely compromised this. We just need to write this shellcode. And so because we want our compromise to be permanent, basically we're just going to write a little piece of shellcode that's going to overwrite a piece of flash, let us hook into the original dongle code, and start sending the serial data that we were talking about earlier. So this is what it looks like. At this point, if we have control over an app, we can control the dongle and the butt plug. If we have control over a butt plug, we can control the dongle and the app, and so on. So we've actually completely compromised the local scenario in the case of the PC app. And it's especially cool because this last vulnerability that I just described actually is absolutely not specific to any of these butt plugs. It's for anything that uses a soft device on that sock. Which is basically everything that uses that sock, and apparently there are a lot of devices that use this old NRF 51822. So we have essentially found a vulnerability that could also be used to compromise every one of those devices, assuming that's configured in a proper way, or like a way that is conducive to exploiting this vulnerability. So that's kind of cool. Finding vulnerabilities potentially in like maybe smart locks or something like that just by hacking a butt plug seems kind of worth it and surprising. But this is the world we do live in at this point. So, question is, we have the ability to compromise an app from the butt plug. What can we do with that? Well, this is we're still just executing JavaScript inside of v11's Electron app. The question is, what does that give us? Because it's 11's and that this is running at medium IL on Windows, it turns out it actually just gives us kind of everything. We can access all the files on the computer. We can execute arbitrary code, just spawn any exe that we want. So we've basically kind of compromised the computer just by doing this, which is kind of great and helpful for us. But the question is from there, even if we can create this ransomware that doesn't just infect the butt plug but also infects the host computer, can we actually make this go kind of viral, right? Because technically we can already compromise the butt plug from a different butt plug or from a different dongle, and that could be something that we could be used like kind of spread this locally. But it would be better if we could spread it over the internet because obviously there would be much more people that you can reach. Now the question is, how do we do that? Well, there are a lot of these social features in the app, such as the chat-based stuff, and the fact that you can just kind of remotely control a toy. So the question is, how does that interface work? Does that allow us to kind of compromise a remote device? Of course, the answer is going to be yes, but how does it work? Basically, well, that's what I was showing at the bottom left there. Is a JSON object that is used to control the device remotely. It's going to have kind of like the type of object that it's supposed to be, and then in this ID mode is going to give the MAC address of the butt plug that is supposed to be controlled, as well as the command. So V means vibrate, and that's what's going to be sent over as JSON to the remote app. Now, how does the remote app kind of use this? The thing that we can kind of think about here is that basically if we're able to somehow hijack this into allowing us to send an arbitrary string over to the dongle, we can actually exploit the dongle JSON parser bug in order to get code execution there and then use that to kind of get code execution back on the app. So it's kind of convoluted, but it turns out it totally works. The reason for that is that it doesn't actually properly check that the incoming data for like the vibrate command is actually an integer. It does try to do that check. If you take a look on the right there at the top, in the ID mode, it does check that n, which is the incoming vibration strength data, is greater or equal than 0. And what that does is that it actually effectively checks that it's an integer that is positive. The reason for that is that if you can take a look on the left there, on JavaScript, if you do 12 is greater or equal than 0, it's going to tell you yes. Even if it's a string, it's going to tell you yes. Now, if it's a string that also includes some text that is not a number, it's going to tell you no, it's not, that's not going to work, so that's going to block us. That's what makes it such that you can't just arbitrarily inject a command into there. However, if you take a look at the bottom there, it has the exact same check, but instead of checking that n is greater or equal than 0, it's checking that n is not less than 0. And the problem there is, well, if you check that it's not less than 0, then yes, the string is also going to tell you this, that it is not less than 0. But if you then, kind of reverse that, it's actually going to tell you it's true, even though it's not an actual string. Well, even though it's not an actual integer. So it's kind of unfortunate. I'm not sure why they decided to like flip that test there, like the filter. But essentially it means that we can inject an arbitrary string into this command that's going to be sent over to the dongle, and that allows us to send the exact same exploit code that we sent over earlier that allowed us to compromise the dongle for the JSON parser. So basically the only difference here is that we can just do it over the internet, basically exploit this firmware bug over the internet just because they flipped a check, which is unfortunate. So at this point, we have actually our viral butt plug worm. It's going to allow us to kind of compromise the dongle, which allows us to compromise the app, and then we can go from app to app. The only problem here is that we can only do this assuming that the remote partner has accepted our request to control our toy. But it turns out you can actually get code execution on the remote app in a much simpler way, which is that they have a chat feature where you just can send text. Turns out you can't just send text, you can also send HTML. So kind of sending the exact same thing as before. Sending this message, you can pop alert. Again, unfortunate, this is kind of very basic web dev stuff because I could find it and I'm definitely not a web dev, so. At this point we can get code execution just by sending a message. So we basically achieved our goal. This is a payload that I end up using. It's going to both spawn a local process to get code execution on the actual device, maybe do some ransomware, and then it's going to also send that message to all your friends and create basically a completely viral exploit here. So we've compromised every node in the network, which is what we wanted to do. So you Yay, go us. And that means that it's time for a live demo. A little tired trying to remember how all of this all works. You can all see this, so please bear with me. So the first thing I'm going to show you is this. I'm going to be actually using BTLE jack to kind of like try to hijack a connection between a butt plug and this VM right here. This VM which hopefully works. Okay. So this VM is just a regular Windows VM. It's connected to the dongle because VMware lets you do that. And I'm going to turn on this butt plug. I hope you can hear it. So this works, it's on, then you can kind of add a toy. Hopefully that's going to work as well. Oh wait, shit, I forgot to do something. Okay, let's start over. Okay, so it did connect, that's cool, but it didn't, I'm a dumbass. Come on. So I actually want to disconnect this because I forgot to start the BTLE jack process on the same side. The only reason that we're doing BTLE jack in this mode is that it's going to be more successful for a live demo, but in theory, well, I mean, not just in theory, actually in practice, we can also hijack an existing connection without having to sniff it while it's happening. So this is just to make things easier. Okay, so now we're going to do this again, connect the toy. Hopefully the sniffers are going to detect that connection. All right, it detected a connection on the left there. That's pretty good. Okay, and then we have this app that's connected to our sex toy. All right, so we can actually control it. I don't know if you can hear it, but it's there. You gotta stop it. Okay. All right, it stopped. From here, we should be able to actually hijack this connection. The way we do that is, I'm trying to remember this. Oh my God. I used to have a mouse for this. It was much easier. Okay, then we copy this parameter. I'm really sorry about this. I'm going to try and make it faster. All right. And T, which means hijack. So we're going to try and hijack this connection here. And if it works, it should kill the connection in this app, and it should just happen. Okay, so it's trying to hijack, it didn't hijack the connection, so that's great. Thank you, BTLE jack, for a great tool. So from here, what you can see is that in here, in the app, it actually disconnected because we now have control over the butt plug from Ubuntu. And so in theory, we should be able to make it, for example, vibrate remotely. No, str, vibrate, 20s, oh, not vibrate, god damn it. 20. Yeah, it's actually happening there. So that works. That's great. Now we're going to put this into DFU mode. Hopefully that also works. It should stop it if it works. There we go. It stopped. Okay, so now it's actually in firmware update mode. So at this point, I take my phone. I'm going to try and connect it. Hopefully it works again. Yeah. All right. Cool. So from here. Please don't look at my apps. Please don't send me any messages right now. So we're going to grab the firmware version for the exploit, version 27. It's a lot of work. And we should be able to say DFU targ. Okay, so now we're going to be flashing this new firmware from our phone. It's updating. Going to just keep this here for now. And from here, what we're going to do, assuming this works. All right, it's been updated. So now what we can do is pull this up and try to connect back to it. Oh, I think it's doing it on its own. Let's see. And so, so this worked. At this point, we have gotten code execution on the dongle and then back on the computer through this. We downloaded an exe from the internet and we ran it. It unfortunately encrypted our butt plug, which, you know, it's unfortunate. It's probably from North Korea. And then what we can see is that I had this other VM which was also running the app. This one is not connected to a dongle or anything, as you can tell. But it is connected to the internet and is like my friend. And so had a message and it just runs the exact same thing. So we've achieved like butt plug virality with this infected butt plug. Don't connect to it right now unless you want to like get your butt plug encrypted. And yeah, I mean that's basically it. The conclusion, well, okay. I think there's a couple lessons that we can learn from this, which is, as I mentioned, as much as this is kind of like a funny line of research, in my opinion, it is actually kind of important to look at the security posture of these devices, not only because it is actually used by people for their livelihoods, but also because, in my opinion, it is kind of very representative of the current state of, IoT and connected devices in general. It's kind of like all these different technologies, which are both new and not new, kind of like working together, and people don't necessarily understand all the implications of like having one vulnerability in one component there is that you can kind of start chaining these things and turn an XSS into a butt plug firmware hack, or like a USB dongle hack that should only be possible locally ends up being exposed to the internet and stuff like that. So hopefully this kind of research applies to other things. And I wanted to say something else, but I completely forgot what it was. So I guess thanks for listening. And if you want to find all the code that was in there, go follow me on Twitter. I'm going to post this on GitHub later today if you want to start hacking your own butt plugs. And I do want to thank all my friends who helped me make this, all my friends who also introduced me to the world of connected butt plugs, who are extremely gay. I'm not going to name names, but you know who you are, Aaron. All right. And thank you very much.